Hey everybody. Today we're talking about data dredging. This is the practice of identifying patterns in a data set through exploratory analysis, typically visual analysis, just making a lot of pictures, but sometimes numerical exploratory analysis as well, and then selectively testing observed trends for statistical significance. It's bad practice because even random data frequently has patterns in it, and if you run enough statistical tests, sometimes you're eventually going to start picking up some of those random patterns just through large numbers. A little bit of key vocabulary here. A type 1 error, or false positive, is when a statistical test concludes that a phenomenon is significant, even though it's really just due to randomness in the sampling procedure. When we talk about the significance level of a test, alpha, usually 0.05, that's encoding the sort of acceptable risk of a false positive. In other words, if you just have random data, what's the probability that you're going to get statistical significance anyway? At alpha equals 0.05, you expect about one false positive out of every 20. When you're conducting multiple tests in a single study, the probability of getting at least one type 1 error grows rapidly. And we call that overall probability the family-wise error rate, FWER. The calculation is shown here. The 1 minus alpha is the probability that an individual test does not show a false positive, when in fact there's not a significant relationship between the variables. So the 1 minus alpha to the k is the probability that k tests do not have any false positives. Subtracting that from 1 gives you the probability of getting at least one false positive in k tests. And this gets big as k gets larger. It starts at k times alpha, approximately, for small k, and then approaches 100% as the number of tests get larger. This becomes a particular problem when you're comparing variables pairwise, when you've got a bunch of variables and you start comparing them by twos. If you have m different variables, then you're going to have to do m choose 2 tests, and that's m times m minus 1 over 2, so, about 1/2 m squared. Here's a table showing how bad it gets fast. If you're using alpha equals 0.05, by the time you've got 6 variables, when you're doing the pairwise tests, you've got more than a 50% chance of getting at least one false positive. By the time you get to 10 variables in your data set, which isn't actually that many variables these days, the probability of at least one false positive is already over 90%. So pretty likely that you're getting at least one. And of course, you could always get more than one. Now, I want to swap over to R and do a bit of a demonstration here to show you a couple places where this sort of data dredging actually happens in practice. Okay, so here I am in R. I'm going to start by loading up tidyverse as usual and setting my theme to minimal. I'm not in love with ggplot's default gray background. I'm going to set a seed for my random number generator so that whatever I do is reproducible by you at home. And in lines, 10 through 15, I'm generating some random data. I'm making 2 data frames, and you can see these just come from random normal variables in each case. I think, I'm going to start with df2, actually, on the spur-of-the-moment decision. Let's just take a look at df2 here, see what it looks like. Okay, so I've got 1,000 random values here, but I've broken them down into groups of 100. And there's group A, B, C, D, etc. There's 10 groups, each with 100 values. So if you're doing an exploratory data analysis, the first thing you might do, for instance, is to get a side-by-side box plot for these. So let's do that. On the x-axis, I'm going to put the categorical variable, that's group. On the y-axis, I'll put the quantitative one, that's value. I don't need anything to be fancy, so I'll just do a basic geobox plot here. And I'll zoom in on that so you can actually see it. Okay, so we know that this is just random data. We can just attribute this to random variation. But if you're just doing an exploratory data analysis, you might be tempted to look, for instance, at groups G and F, G and H, and say, oh, look, there's a real difference here. So maybe we should do a t-test between those two. Let's actually do that. The way I'm going to do that is by getting a smaller data set. So I'm going to filter df2 so that group is in this vector that I'm now going to specify capital G and capital H. And so for instance, if I view df2 small, you'll see I now only have 200 entries, and there's only G and H. All right, so let's actually do a t-test now using df2 small. And I guess I should say data equals. Let's be really explicit. And the formula I want, which I usually put first, is going to be is value explained by group. Sorry, I'm kind of coding this in reverse here. There we go. So let's see what we get. And I'll zoom so this printout looks a little nicer. All right, so you can kind of see the p-value here. I really want you to be able to see it as a p equals. The p-value here is 0.007885. So not infinitesimal, but very small, certainly lower than your typical significance level cutoff of alpha equals 0.05. So this is a situation where you have detected a pattern in some random data simply by the fact that you've visually done a lot of different tests. We homed in immediately just on G and H, but whether you were thinking about it or not, you kind of dismissed out of hand the difference between A and B and C and A and C and so on. So even though we're only running one t-test, for all intents and purposes, we really are doing multiple comparisons. So this p-value is not one that you should report. Perhaps it helps you generate a hypothesis. Maybe you go out and gather more data to look at these two groups, G and H, to see if there's actually a difference, but you're not justified in any sort of formal inference here. Okay, so the next thing I want to look at here is df1. So maybe I'll put a new comment. Correlations, which only has 2 R's. There we go. So let's look at df1 now. And I'll close up some of these other windows. Okay, so this time I've done something slightly different. This time I've gotten 10 variables, v1 up to v10, and each one has 100 entries. So we can imagine these as sort of 10 different explanatory variables in an observational study, for instance. And I'm going to wonder, are any of these correlated or not? So we can get a correlation matrix on this just with COR, and if we just feed it df1, we're going to get all the different correlations here. So I'll give you a slightly better view on this. Because I'm zoomed in, it's never going to be beautiful. But you can see here at the top, for instance, I've got the correlations between variable 1 and all the other variables. Obviously, there's 100% correlation between v1 and v1. Similarly for v2, and so on. Now, some of these values are very small, of course, like v1 and v2 is 0.08. Random noise, we get that kind of correlation. Others of them are a little larger, like 0.144. And as you glance through this, you'll see some that are even larger than this. I mean, correlations here are going to have some random distribution. This is occurring just by these correlations are occurring as a result of a random process. The cutoff in this case for significance at alpha equals 0.05 is 0.197. And I am not going to do that math. I have a slide on it. Let me just show it to you really quickly. There it is. If you want to pause the video and look at this, feel free. I have a whole video on correlation testing. I will throw a link to that up top. I don't want to go through the math for it right now. Suffice it to say, if we get a sample correlation that's greater than 0.197 or less than negative 0.197, that would qualify as statistically significant at alpha equals 0.05. So what I want to do now is just to see how many variables here have a correlation value greater than 0.197 in absolute value. So, I don't think I'll actually do a computation here. We can leave that as an exercise to use some code to figure out how many of these are greater than 0.197 in absolute value. So here we have 2 of them exactly. Remember, order doesn't matter. So V2 and V10, for instance, will also appear as V10 and V2. And you can see the correlation there is about almost 0.3, so a little bit larger. So what we're seeing here is that we have 2 false positives between these 10 variables. And if you are not thinking in terms of protecting yourself against data dredging, you could falsely conclude that there's a real relationship between these variables. When, of course, in reality, all you should be able to conclude here is that maybe you should investigate these particular pairs of variables a little bit further. A few more comments as I wrap up. There are statistical techniques for dealing with multiple tests, like the Bonferroni correction, for instance, is the oldest and best known, I think, to data amateurs. While those things do exist, it is really always best to separate out exploratory analysis from formal inference, and to use different data sets for each. I think a lot of times we get hypnotized by p-values and by statistical inference, when really you don't always need one of those at the very end to draw a conclusion. Obviously, for some publications and for some purposes, these things are really, really important, but we should not underestimate the value of exploratory data analysis. Just to draw a little bit more attention to the distinction, you should use exploratory data analysis to generate hypotheses, refine your research questions, and determine directions for further work. All very important things. Use formal inference to check whether specific, previously stated hypotheses could be plausibly due to random chance, or whether those hypotheses are likely due to something actually happening distinct just from random chance. One last note as I complete this vid. There are plenty of applications where p-values are used for model building or other purposes. And the one that comes immediately to mind for me is when you're selecting variables in a regression model, using, for instance, backward stepwise selection. When you're using p-values in this way, you have kind of spent your p-value budget, and you should resist the temptation to also treat them as measuring significance. That's a sacrifice you make when you use p-values for that model building. Once again, you'll need new data if you want to actually do some inference.